to record this talk. Robert, I presume that is fine with you.
Yes.
Good evening, everyone. My name is L. Sriram Kumar. I'm a faculty at the Department of Physics at the Indian Institute of Technology, Madras. I'm part of the newly instituted Center for Strings, Gravitation, and Cosmology. And as a part of the activities of the center, we have initiated this new series of lectures called the Chandrasekhar lectures. And today we have Professor Robert Brandenberger from McGill University, Montreal, Canada, to give the inaugural Chandrasekhar lecture. Before I introduce Professor Robert Brandenberger, I will request the head of my department, Arul Lakshmi Narayanan, to say a few words. Arul.
Thank you, Sriram. And first of all, welcome to all of you for this inaugural lecture. And I'm very happy to that we have a distinguished speaker, but more of that later. I want to first say a few words about this center itself and similar centers. As you know, IIT Madras is now an institute of eminence, as it was declared last year. Subsequent to that, there's been formation of several focused centers for various research activities have been identified and funded under the Institute of Eminence scheme. There are a few, so within the physics department, there are several such centers, but there are two major theory centers. And one of it is this Center for Strings, Gravitation, and Cosmology. And this comprises of several of our faculty members and will initiate a series of activities, as Professor Sriram will probably tell us shortly. But also, the center, as it says, for strings, gravitation, cosmology, has string theorists, as cosmologists and gravitational physicists, and it kind of reflects our, department's range of activity. In particular, Professor Suresh Varadarajan and Dr. Ayan Mukhopadhyay are string theorists who are part of this. Dr. Dawood Kotawala and Chandrakant Mishra come from classical quantum gravity and gravitational waves part of it. Professor Sriram Kumar himself specialized in gravitational cosmology. So, being a theoretical group, the primary activities of such a center is to increase academic interactions, both between collaborators and ourselves, as well as actually encouraging, visitors of various kinds, both national and international. But also, really, most importantly, especially for this program, the center is conducting lectures, schools, and workshops every year, and on different topics of the center's interest. So it's an outreach program, which I think is one of the, this particular thing is an outreach program, which is one of the, I think, really a need of the hour. So I'm really happy that this inaugural lecture is there, and by a distinguished cosmologist, Professor Robert Brandenberger. So welcome again, and we look forward to the lecture today. And I believe there will be 3 more lectures, but let me hand over now Professor Sriram again to introduce formally Professor Brandenberger. Sriram.
Thank you, Arun. Before I hand over to Professor Brandenberger, let me say a few words about him. We are indeed glad to have him give the inaugural Chandrasekhar lecture. Professor Robert Brandenberger is presently a Canada Research Chair, Tier 1 at the Department of Physics, McGill University, Montreal. He had completed his PhD at Harvard University in 1983, after which he had worked as a postdoctoral fellow, initially at the University of California, Santa Barbara during 1983-85, and later at the University of Cambridge during 85 to 87. Professor Brandenberger had joined the faculty of Brown University in 1986 and then moved to McGill University in 2004. He has worked on a wide range of issues in cosmology, and he is well known for his work on inflation, as well as constructing possible alternatives, such as the string gas cosmology. Professor Brandenberger has won numerous awards for his work, including the Alfred Sloan Research Fellowship, the Outstanding Junior Investigator Award from the Department of Energy, the Killam Research Fellowship, and the CAP CRM Prize for Mathematical Physics. He's a fellow of the American Physical Society and a fellow of the Canadian Royal Society. Today, he will be speaking to us about towards an understanding of the evolution of the very early universe. Robert, over to you.
Okay, so can you hear me?
Yes.
Good. So first of all, I would like to thank the organizers for inviting me to give this inaugural Chandrasekhar lecture. It's a great honor for me to be able to do this. And I'm also happy to be able to contribute to launching this new Center for Strings, Gravitation, and Cosmology. In fact, I will try to convince you in this lecture that there's a very close connection between string theory and early universe cosmology. Now, I realize that many of you in the audience are students. And so I will start out with a fairly long introduction in which I will try to persuade you that cosmology, and in particular early universe cosmology, is an exciting field. After doing this, I will talk about general criteria for a successful early universe cosmology. And then after that, I will move on to a brief discussion of the standard paradigm for early universe cosmology, a paradigm which has been in existence for 35 years, namely the inflationary scenario. But I will point out that this scenario is facing quite severe challenges, in particular if you come from the string theory point of view. So I'll try to persuade you of this point. And if you accept these arguments, then at the end of the lecture, hopefully you'll be willing to listen to some very speculative ideas of how string theory could impact early universe cosmology in quite exciting ways. So this is the outline of what I want to discuss. Good. Let me start with the introduction. So cosmology is actually a very old field. For millennia, humanity has wondered about the origin and early evolution of the universe. And nowadays, we would phrase these mysteries, these questions about the origin of the universe, we would phrase these questions in the following way. What is the Big Bang? Was there a Big Bang? What was before the Big Bang? So these are millennia-old questions which humanity has asked. But what has changed recently is the fact that we have data. Now, the data that we have comes to us from beautiful instruments like this optical telescope, which is high up in the Chilean Andes. And with this optical telescope, we look at the sky. And the first thing that we see when we look at the sky through such telescopes is we see galaxies, assemblies of billions of stars which have a rotational structure. But I'm not interested in galaxies, but I'm interested in what is beyond galaxies. So let's look beyond galaxies. Let's look at the sky beyond the galaxies. And let's represent each galaxy just by a point. And let's ask, what is the distribution of galaxies in the sky? So here what you see is a projection of the sky onto a plane, like the projection of the surface of the Earth onto a plane. In the equatorial plane, this is the Milky Way. This is the North Galactic Pole and the South Galactic Pole. And what I want you to take away from this picture is that there are a huge number of galaxies, but there are certain regions in the sky where there are few galaxies and other regions in the sky where there are many galaxies. So this is one aspect of what I call structure of the universe. Now, we can also probe the universe in different wave bands. So it was discovered in the 1960s that the universe is glowing in the microwave. And here is a picture of a microwave telescope, which is again located in a quite remarkable place on the surface of the Earth, namely on the South Pole. And there are also telescopes in outer space, like the WMAP telescope, which probe how the universe is glowing in the microwave. So with these expensive telescopes, we look at the intensity of the microwave background in different directions in the sky, and we see this picture. So you see different colors indicate different temperatures. And again, this is a projection of the sky onto a plane. So each point corresponds to a direction in the sky, and the intensity of the microwave background is converted to temperature. And so what should impress you is this isotropy of the cosmic microwave background, this incredible isotropy. This is a fact of nature. Now, if we probe the microwave to much higher resolution, to better than 1 part in 10,000, then we start to see anisotropies popping out, hot spots and cold spots. And if we expand this map in spherical harmonics to quantify this data, so spherical harmonic number in the horizontal axis, power on the vertical axis, then we get the quantification of the data. So an isotropic distribution would be 0 for all angular scales. And you see that there's very interesting structure. There's a peak at 1 degree, and there's some ringing at smaller angular scales. So the black are the data. There are some statistical uncertainties on small angular scales, and there's a systematic uncertainty on large angular scales. So this is this beautiful data. And there's an artist who was asked to draw a 6-parameter fit to the data. And this red curve is a 6-parameter fit to the data. And I'm going to tell you who the artist was in a couple of minutes. So you see, the new challenge for cosmology is to come up with an explanation of the observed large-scale structure. So we want to understand the origin of the patterns in the distribution of galaxies. And we also want to understand the origin of these anisotropies in cosmic microwave background maps. And finally, we want to make predictions for future observations. And there are going to be lots of future observations. There are bigger optical telescopes, which are coming online. There are new missions to explore the cosmic microwave background. But then there are also new windows to probe the universe, which are opening up. For example, the 21-centimeter window. So the universe is also glowing in 21 centimeter. And 21 centimeter, that's the hydrogen hyperfine transition line. And before stars form, most of what turns into the visible matter was neutral hydrogen. And so by mapping out the 21 centimeter radiation that comes to us from the sky, we can map out the distribution of neutral hydrogen in the early universe in the dark ages before stars have formed. And since I'm here in Canada, I want to show some pictures of telescopes with Canadian involvement. So here is the CHIME the CHIME 21 centimeter telescope, which is located in Western Canada. This is the first telescope which is actually taking data. And then there are telescopes with Canadian involvement in South Africa, for example, the HIRAX 21 centimeter telescope, the HERA 21 centimeter telescope. There's also a 21 centimeter telescope at the windiest point on the surface of the Earth, which is Marion Island, which is halfway between South Africa and the Antarctic. And in fact, there are also Indian telescopes, which are probing the global aspects of the 21 centimeter universe. So these are new observational windows which are opening up, and we would like to make predictions for what these telescopes will see. Okay, so now all of this data we want to describe in some theoretical context. And the first theoretical context is standard Big Bang cosmology. So we know from the existence of the microwave background that the universe has been expanding for a long time. So the universe starts in a plasma state. I'm not saying the universe starts with a Big Bang, but I say far in the past, the universe was a hot plasma. At some point, the plasma recombined. It formed neutral atoms. And at that point, the microwave background was released. So standard Big Bang cosmology, which is the old paradigm of cosmology, is based on three assumptions. The first assumption is that space and time are described by Einstein's theory of general relativity. It's a classical theory. And that matter is described by a superposition of classical matter sources, namely the radiation, which we see in the microwave background, which has pressure 1/3 times the energy density, and the stuff that forms galaxies that we model simply as pressureless matter, cold matter, so pressure is equal to 0. So in standard Big Bang cosmology, we have these two fluids. And finally, standard Big Bang cosmology assumes that space is homogeneous and isotropic on large scales. So it is described by this metric. So this ds squared describes the separation of space-time events. T is physical time. X are the coordinates which are painted onto the expanding universe, onto the expanding space. And A of t is a scale factor which describes the radius of a piece of the expanding universe. So these are the assumptions that go into standard Big Bang cosmology. And the big successes of standard Big Bang cosmology is that it explains why space is expanding. It predicted the existence and black body nature of the cosmic microwave background. And it also predicts the abundances of light elements. And I want to go quickly over the next slides. I just want to show you the data underlying these successes. So here's a modern plot of redshift versus distance of supernova. And you see that there's a roughly linear redshift distance relationship, which confirms the fact that the universe, that space is expanding. And going back to this picture of standard Big Bang cosmology, which posits that the universe started in a plasma state, and then the plasma cooled down and eventually the universe recombined. And it is at this transition that the microwave background was produced. So standard Big Bang cosmology predicts the existence of the microwave background, and it predicts that the microwave background has a black body distribution. And I want to emphasize this point. So if you look at one direction in the sky, and you look at the intensity of the microwave background as a function of wavelength, then what you find is this curve. And this curve includes the observational error bars. So this is a spectacular black body. And so this is the most important success, in my opinion, of standard Big Bang cosmology. It predicts this black body nature of the microwave background to this incredible precision. So with this curve, cosmology has become a precision science. However, we shouldn't just rest on the laurels. We should go and see what does the theoretical paradigm not explain. So the theoretical paradigm does explain the abundances of of light elements, because if we go further back in time, then we are in the ages where nuclear physics processes are in equilibrium, and that gives you the successful explanation of the abundances of helium, deuterium, and lithium. So there's a range of this one parameter that we have in standard Big Bang cosmology, which is the ratio of baryons to photons. There's a range of this values of this one parameter for which we can fit all these three curves. But I want to go back and focus on this curve. So this is the biggest success. However, what this model does not explain is the fact that the microwave background is isotropic. So the isotropy of the microwave background cannot be explained by standard Big Bang cosmology. So standard Big Bang cosmology offers no explanation for the large size and for the large entropy of the universe, no explanation for the fact that the universe appears to be spatially flat, no explanation for the isotropy of the microwave background, and no explanation for the origin of any of this interesting structure, which I showed to you at the beginning. Microwave anisotropies cannot be explained. The distribution of galaxies cannot be explained in the context of standard Big Bang cosmology. So we have to look beyond. And here's a brief illustration of why standard Big Bang cosmology does not explain the isotropy of the microwave background. So the vertical axis is time, the horizontal axis is space, and this is the time when the universe underwent the transition from a plasma to being neutral. This is when the microwave background was released. And this curve here, this diagonal curve, this is the horizon at the time of recombination. This is how far information can travel from the Big Bang until the microwave background is released. And this curve here is how far back we see the microwave background. So the time of recombination is about 300,000 years, but we are now 13 to 14 billion years after the Big Bang. So we are seeing the universe being isotropic over a much larger scale than the scale which could have been in causal contact in standard Big Bang cosmology. So no causal explanation for the origin of isotropy of the microwave background. And this plot shows you that there is no explanation for the origin of structure in the universe. Okay, so students, beware. I'm sneaking in 2 lies in this explanation. You are not allowed to look up any textbooks, even the textbook by Padmanabhan, because all these textbooks say the same thing that I will say. They all contain these 2 lies. Okay, so let's continue with these 2 lies. We see today structure which is non-random on very large scales, not too much smaller than the standard Big Bang horizon today. So this is the wavelength on which we see non-random structure. Here I'm drawing co-moving coordinates. So these are coordinates which expand as the universe expands. I want you to view fluctuations as waves, density waves. So we want to explain the amplitude of the density wave on this scale. We go back to the time of equal matter and radiation. And if there is non-random structure today, there had to have been non-random structure at the time of equal matter and radiation. But as you see from this diagram, this length scale at equal matter and radiation is larger than the causal length. So standard Big Bang cosmology cannot explain the origin of any of the observed structure in the universe. And for students who've identified the lies, either email me or email Sriram. Okay, so to solve these problems of standard Big Bang cosmology, we have to modify the history of the universe, and we have to modify the history of the universe at very early times before the time of nucleosynthesis, because we don't want to mess up the successful predictions of nucleosynthesis. So early universe is required to explain structure in the universe today. Okay, so now I want to discuss criteria for a successful early universe cosmology. And by successful, I mean a early universe cosmology which can explain the isotropy of the microwave background and which can explain the origin of structure. So in particular, a model which can explain the red curve. So now who first predicted this red curve? Now, there are 2 groups who predicted this red curve in 1969, 1970. And for those of you who are in cosmology, I want to stress that this is 10 years before the development of inflation. And here's a plot from the paper by Zeldovich and Zuniaev of 1970. And this plot shows the time, vertical axis, space, again, co-moving coordinates, horizontal axis. This diagonal line is the standard Big Bang horizon. And what Zeldovich and Zuniaev and in parallel Peebles and you pointed out is the following. If you start with fluctuations, so plane wave density fluctuations on all scales at early times with a roughly scale invariant spectrum, so the amplitude of the wave, of the density waves, is roughly independent of scales, then these authors pointed out that these density waves will remain frozen in until the wavelength becomes smaller than the horizon. And then they will start to oscillate. And they will oscillate until recombination when the microwave background is produced. So the density wave which crosses the horizon at recombination has done 0 oscillations. So we catch this density wave at its maximum extent, whereas the density wave which has done a quarter of an oscillation, we will catch it at 0 amplitude, maximal velocity. The wave that has done half an oscillation, we will catch it again at a maximum of the extent. And it is this feature of different different periods of oscillations. This explains this oscillatory pattern in the angular power spectrum of the microwave background. So this is the mode which has done 0 oscillations. This is the mode which has done a quarter of an oscillation. This is the mode that has done a half an oscillation. So this physics was understood 10 years before inflation. So given a roughly scale invariant power spectrum of fluctuations on superhorizon scales before equal matter and radiation, and this spectrum was known to, at that point, to give a fairly good description of the structure of galaxies. And this predicts the acoustic oscillations in the angular power spectrum. And it predicts more because this plot of the Zeldovich-Zuniaev paper had a second part. And the second part shows you the matter power spectrum as a function of wave number. And these oscillations, which are described here, also gives rise to oscillations of the matter power spectrum. And this is called baryon acoustic oscillations. So all of this physics, the acoustic oscillations in the CMB angular power spectrum and baryon acoustic oscillations in the matter power spectrum, was understood 10 years before inflation. But the one question which was not understood in 1969 and 1970 is how does one obtain such a spectrum of density perturbations on super horizon scales? And inflationary cosmology is the first scenario based on causal physics, which yields such a spectrum, but it is not the only one. So now I want to turn to the criteria which a successful early universe cosmology has to satisfy. And here I have to introduce to you the difference between the horizon and the Hubble radius. So the horizon, the way I define horizon here, it's the forward light cone of a point on the initial Cauchy surface. Let's say, loosely speaking, I can say at the Big Bang. So the horizon gives you the region of causal contact. Now the Hubble radius is something very different. The Hubble radius is the inverse expansion rate. And the Hubble radius is relevant to the dynamics of density perturbations. Because it turns out, if you study the theory of density perturbations in an expanded universe, you find that density perturbations with a wavelength larger than this Hubble radius are frozen in. They don't oscillate. But density waves on a length scale smaller than the Hubble radius, they oscillate. So if you're interested in how density perturbations evolve, it is a Hubble radius that's important. if you're interested in causality, it's the horizon which is important. Now, in standard Big Bang cosmology, the Hubble radius and the horizon are the same, and therefore there is a horizon problem. Therefore, standard Big Bang cosmology cannot explain the isotropy of the microwave background. So in any theory which can provide a mechanism for solving the horizon problem, the horizon has to be much bigger than the Hubble radius. So here comes a list of criteria for a successful early universe cosmology. The horizon has to be much, much bigger than the Hubble radius. Otherwise, you can't explain the isotropy of the microwave background. Now, if you want to causally produce density perturbations in the early universe, then the scale on which you want to produce the density perturbations has to be smaller than the Hubble radius at early times, because you want to move around matter on a scale which is smaller than the expansion rate. So that's the second key criterion. And the third criterion is that if you can satisfy these first two criteria, then the mechanism that you invent to produce fluctuations has to produce a roughly scale-invariant spectrum of curvature perturbations. So these are the three criteria for a successful early universe cosmology. Now, I will show you three ways of satisfying these criteria. And one way is indeed cosmological inflation. And as I will tell you in a little bit more detail a little bit later on, inflation is based on the hypothesis that there was a period in the early universe. So here the vertical axis is time. 0, that's the Big Bang. And this period between T sub I and T sub R, that's this hypothetical period where space is supposed to expand almost exponentially, the period of inflation. And after inflation, the universe evolves as in standard Big Bang cosmology. So the horizontal axis is space, physical space dimension. And what happens to the horizon? During the period when space expands exponentially, obviously the horizon expands exponentially as well. So it's this dash curve, which is the horizon. Now, during this period of exponential expansion, the expansion rate is constant, and therefore the Hubble radius, which is the inverse expansion rate, is constant. So during inflation, the horizon becomes exponentially larger than the Hubble radius, and therefore, if inflation lasts long enough, you can easily make the horizon bigger than the region over which we see isotropy of the microwave background. So criterion 1 is satisfied. Now, this red curve indicates the wavelength of a density perturbation. For example, the wavelength that corresponds to the quadrupole of the microwave background. And during the period when space expands exponentially, the wavelength of a density wave also expands exponentially. And so from this sketch, it is clear that if inflation lasts long enough, then the scale that produces the quadrupole of the microwave background starts out smaller than the Hubble radius. Therefore, the second criterion is satisfied. Now, during inflation, the energy density is constant, even though space is expanding exponentially. So because the energy density is constant, there is a time translation invariance in this phase, and therefore the waves that are produced, the density waves, any mechanism that you can imagine that produces density waves in this period will produce a scale invariant spectrum of cosmological perturbations, as was first pointed out by Bill Press in 1980. So here's a scenario with which you can satisfy all three of the criteria, but it is not the only one. Here I'll present you a second scenario. So here we assume that you have a bouncing universe. This is the size of space, this scale factor. This is time, the horizontal axis. And I'm assuming that the universe started in a contracting phase. There was some new physics that goes beyond general relativity and usual matter that gives you a bounce, and then we emerge in standard Big Bang expansion. So this is a corresponding space-time diagram in the top. Vertical axis time, horizontal axis is co-moving spatial coordinates. This diagonal curves the Hubble radius. The Hubble radius is decreasing the contracting phase. It's increasing the expanding phase. Time runs from minus infinity, plus infinity. The horizon is infinite. Therefore, criterion 1 is satisfied. If you go far enough back into the past, all scales that we see today start out sub-Hubble. Therefore, criterion 2 is satisfied. And it turns out that if this period is a matter-dominated period, then initial vacuum fluctuations also develop into a scaling around spectrum of fluctuations. But I'm speaking fast here because that's not relevant for the rest of the talk. So bouncing cosmologies can provide a second scenario of a successful early universe cosmology. Now, the third scenario is based on the idea of an emergent universe. So this is based on the idea that there was a phase in which maybe space-time didn't even exist, a quantum gravity phase, which I will here model as a phase where the universe has constant size, constant scale factor. Then there was a phase transition to standard Big Bang cosmology. So this is the assumption I'm making, scale factor as a function of time. And this gives rise to this space-time diagram, time, space. This is this emergent phase. T sub r is a phase transition. After the phase transition, standard Big Bang expansion. The horizon is infinite, so there's no causality problem. In blue, I plotted the Hubble radius. The Hubble radius tends to infinity in the emergent phase. And in the standard Big Bang phase, it is like in standard Big Bang cosmology. So here in red, I show the physical wavelengths of different scales of density perturbations. And you see that obviously these scales start out sub-Hubble. So therefore, a causal generation mechanism is possible. And as I will tell you towards the very end of the talk, if I assume that this emergent phase is a phase with a hot gas of strings, and I have thermal fluctuations, I get a scaling down spectrum of perturbations. Okay, so the message I want you to carry away from this part of the talk is that there is not just one successful scenario of early universe cosmology, but there are several. So let me now turn to the inflationary scenario, which, as I told you, is a scenario which is based on the assumption that there's a period of nearly exponential expansion of space during the early universe, between time t sub I and time t sub r. Now, if you want to get the right amplitude of density perturbations, microwave anisotropies, without tuning your particle physics model, then it turns out that inflation must take place at a very high energy scale. And this energy scale is only a couple of orders of magnitude lower than the Planck scale. And it is maybe 12 orders of magnitude removed higher than energy scales which are probed in laboratories. So this is a timeline. This is another representation of what inflation does. Inflation takes a very small universe and makes it large. So if you compare, if you take our universe backwards in time without inflation, then it had to start out large. With inflation, it starts out small. Now, how do we get inflation? Well, okay, let's first remind you of the successes of inflation. It renders the universe large, homogeneous, and spatially flat. So it's a solution of the horizon and flatness problems of standard Big Bang cosmology. So we can argue that during the phase of exponential expansion, classical matter redshifts. And so matter turns into a vacuum. And therefore, the only fluctuations that operate are quantum vacuum fluctuations. And as Chibisov and Mukhanov for density perturbations and Starobinsky for gravitational waves pointed out, quantum vacuum perturbations evolve into an approximately scaling invariant spectrum at late times. And in fact, the these calculations make the prediction that you get a small red tilt both for density perturbations that has been observed and for gravitational waves, which has not yet been observed. So red tilt means slightly more power on larger wavelengths than on smaller wavelengths. So these are successes of inflation. So how does one obtain inflation? One needs, if one works in a context of general relativity, one needs matter which has pressure smaller than -1/3 energy density. So in fact, to get exponential expansion, you need pressure equals minus energy density. Well, how does one get it? Usual matter doesn't do the trick. So we use the only trick that we have if we work at the level of effective field theory, namely we introduce a scalar matter field. And the potential energy of a scalar matter field can give us this equation of state: pressure equals minus energy density. But one has to ensure that no other contributions of the scalar field to energy dominate. So therefore one has to have the scalar field roll in very slowly, and it has to roll so slowly that I spelled the roll with 2 L's. So quantification of this is V prime over V. So V is the potential of a scalar field. V prime is a derivative of the scalar field with respect to the scalar field value. So this scalar field has to be very flat in Planck units. And the scalar field also has to roll over large distances unless you want to have fine-tuned initial conditions. So I'm skipping the next slide. Okay, so this is what we need. We can get inflation if we have a scalar field with these very special initial conditions. And now I'm going to try to argue that this is unnatural. And here I should warn the students that I will now turn to topics which are controversial. In everything I told you so far, things are not controversial and they should not be controversial. But now I will turn to things which are controversial. So what are problems that persist in the inflationary scenario? Well, there's still a singularity. Inflation takes place at energy scales too close to the Planck scale to trust the effective field theory description of matter and classical gravity. So I will argue here that we really need quantum gravity or string theory to describe the very early universe. And there is a more serious problem. And here I go back to my space-time diagram of inflation. And as Jean-Martin and myself argued 20 years ago, if inflation lasts only a little bit longer than it needs to last in order to solve the problems, then the length scales of everything we see in the universe today starts out smaller than the Planck length at the beginning of inflation. And we know that on length scales smaller than the Planck length, we cannot trust effective field theory. We cannot trust classical gravity. So our theory that we use to describe inflation breaks down. Now, based on this picture, recently, Bedroya and Waffa made a postulate, which is called the Transplantian censorship conjecture. And they postulated the following. They said that no cosmology, which is consistent with a consistent ultraviolet theory of nature, can have the feature that Transplanckian modes ever exit the Hubble horizon. So this is a metric which I showed you before. I remind you that this is the Hubble radius, the expansion rate. The Hubble radius is the inverse of that. And the Transplanckian censorship conjecture says that if you start at any initial time t sub I with a Planck length, and you let that length expand until a later time t sub r, then the length that you get has to remain smaller than the Hubble radius at this later time. So this is the mathematical form of the Transplanckian censorship conjecture. Now, what is the justification for this? Well, I would justify this in analogy with Penrose's cosmic censorship conjecture. So all of you who've taken a class on general relativity will know that black holes with a small charge have a horizon. So if you take a black hole, which sits here at r equals 0. We are an observer far away from the black hole. Well, at the point of the black hole, there's a singularity. But if we take black holes with charge smaller than the mass, then we are hidden from the bad physics, from the singularity, from the non-unitarity. We are hidden from this bad physics by the horizon. Nothing can escape this black hole. But Einstein's equations allow for black holes with charge greater than mass. And for such black holes, the observer far away from the black hole is not hidden from the singularity. So therefore, this is a setup where you run into singularity problems and unitarity issues. So let's recap. General relativity allows for solutions which have time-like singularities, super extreme black holes, for which there are all kinds of problems. And therefore, Penrose conjectured that the correct ultraviolet physics that completes general relativity should prohibit these pathological solutions. They should shield the external observer from the singularity and non-unitarity by the horizon. So now let's take Penrose's argument and let's make the following translation. Position space for Penrose becomes momentum space for cosmology. The singularity of a black hole becomes the space of Transplantian modes for cosmology. The black hole horizon becomes the Hubble horizon. So Penrose translated would then tell us that an observer measuring super Hubble modes must be shielded from effects of Transplantian modes. So this is the Transplantian censorship conjecture. So why do we take the Hubble horizon as the thing that generalizes the black hole horizon? Well, the reason we do that is that fluctuations only oscillate on sub-Hubble scales, whereas they freeze out and become classical on super Hubble scales. And we basically want the classical region to be insensitive to the Transplantian region. So this is a conservative assumption. So this gives us the Transplantian censorship conjecture. Okay, so there's another justification for the Transplantian censorship conjecture, and this is based on the unitarity problem of effective field theory in an expanding universe. So if we do quantum field theory in an expanding background, quantum field theory is described by one harmonic oscillator for each Fourier mode. There has to be an ultraviolet cutoff. The ultraviolet cutoff has to be fixed physical scale. And in an expanding universe, fixed physical scale corresponds to a time-dependent co-moving scale. It is co-moving scales which are being quantized. And therefore, in an expanding universe, you have to continuously create modes if you want to maintain a fixed physical ultraviolet cutoff. And that's extremely non-unitary. And if we want classical physics to be insensitive to this non-unitarity, then we need to impose the Transplantian censorship conjecture. So what does this imply for inflation? So here's my space-time diagram of inflation. So this initial period, it's a period of inflation, post-inflation. I hope you can all see my cursor. And here in this diagram, I showed the Transplantian censorship conjecture to be marginally satisfied because I'm taking the Planck length at the initial time of inflation to evolve until the Hubble radius, but not bigger than the Hubble radius at the end of inflation. If it's not bigger than the Hubble radius at the end of inflation, it will remain smaller. But inflation has to be successful. So the present Hubble radius has to emerge from inside of the Hubble radius at the beginning of inflation. Otherwise, we can't causally produce a structure. And I showed this to be marginally satisfied here as well. Now, you see, the higher the energy scale of inflation, the closer this Hubble radius is to the Planck length. So again, this length is the Planck length. This is the Hubble radius. The higher the energy scale of inflation, the closer the Hubble radius is to the Planck length, and the harder it is to be consistent with both criteria. So the TCC implies this condition on the energy scale of inflation, demanding that inflation yields a causal mechanism of structure formation, leads you to this mechanism, and I will ask you to accept that this implies that the energy scale of inflation has to be smaller than 3 times 10 to the 9 GeV, which is orders of magnitude smaller than what it has to be for simple inflationary models. What does this imply? This implies that standard inflation is ruled out. For dark energy, it implies that dark energy cannot be a bare cosmological constant. Okay, so there's another way of attacking inflation, and this comes from string theory. So if you work at the level of effective field theory and classical gravity, you can do anything you want. You have a huge landscape of possibilities. Any space-time dimension goes, any number of fields, any shape of potential, any field range. Superstring theory is very constraining. It tells you that only a very small subset of all effective field theories is consistent with string theory. The rest lies in the swampland. And so this is a picture of this huge swampland of effective field theories. There is this ultraviolet complete theory, string theory, and this says that only small islands stick out from this swamp, and we need to live in these small islands. And the conditions on these islands are that if the island contains scalar fields, then the range of this scalar field has to be smaller than Planck length. And either the scalar field has to have a steep potential or a sufficiently tachyonic potential. And you see that these conditions are exactly the opposite of what we need for standard slow roll inflation. So standard slow roll inflation is in conflict with the swampland criteria. Eternal inflation is in conflict with the slow roll criteria. Dark energy cannot be a bare cosmological constant. And even quintessence is starting to be constrained, and future data will be able to further constrain quintessence. Okay, so you see, I've used a lot of my allotted hour, and given that, so if you accept what I told you in this part of the talk, that inflation is in trouble, then we really should seek out new ideas. And here I will turn to string theory. First of all, I should mention that bouncing cosmologies are completely consistent with the Transplantian censorship conjecture, as long as the energy scale of the bounce is lower than the Planck scale. And the same is true for emergent cosmologies. And if you can get a bouncing cosmology or an emergent cosmology from string theory, then you'll be in very good shape. So here are attempts to do this. And you see, a talk should end with things which not even the speaker completely understands. So here I will turn to topics which not even the speaker is understanding completely. So let's imagine that instead of having a gas of point particles in the early universe, we have a gas of strings in the early universe. And give me the freedom to take space to be compact, like a torus. Then if we compare a gas of strings with a gas of point particles, we have some crucial differences. So strings have degrees of freedom, with point particles do not have. Strings have oscillatory degrees of freedom and winding modes. So given the fact that strings have oscillatory degrees of freedom, you can show that a gas of strings has a maximal temperature. So you compress a gas of strings as opposed to a gas of point particles. The temperature can never exceed a limiting value called the Hagedorn temperature. This implies no temperature singularity in the early universe if you start from string theory. Now, if you take your finite space, your toroidal space, you can wind it with strings. And this leads you to a symmetry, which is physics at large radii is completely equivalent to physics at small radii if you simply interchange momentum modes, center of mass motion of strings, with winding modes of strings. I don't want to talk. I can come back to this in the discussion session. So if you take your box of strings with radius r, and you plot the temperature of this box of strings, then you start with a large box, you compress, the temperature rises. As the temperature approaches a Hagedorn temperature, you start to excite oscillatory modes, temperature levels off. This size of the box becomes smaller than unity and string units, and then the energy will flow into the winding modes, temperature will decrease. And you see, if the entropy of the universe is large, you have a large plateau, and that motivates this picture. In this large plateau, you will have an emergence phase. So here I'm arguing with this picture, I'm arguing that if you start with string theory, you might very well get this picture of an emergent cosmology. And if you get this picture of an emergent cosmology, you get this space-time diagram, and you can compute thermal fluctuations of the gas of strings. So you do this following, you apply this following method. In the emergent phase, you compute the matter fluctuations, energy density fluctuations, pressure fluctuations. Then for each scale, when the scale crosses the Hubble radius, you convert the induced gravitational waves and curvature perturbations, and you evolve to the present time. And then you can compute the present time density perturbations and present time gravitational waves from, so the curvature perturbations and gravitational waves from the density perturbations and pressure perturbations. So it's a very well-defined procedure. String theorists will tell us what these quantities are. These quantities have holographic scaling. Holography, I mentioned this for the string theorists in the audience. You do the calculation, and what do you get? You get a scale invariant spectrum of density perturbations, curvature perturbations, like for inflation, with a slight red tilt. And this is the expression. You get a particular amplitude, which agrees very well with what observations show us if the string scale is about 10 to the 17 GeV. And you go on and you compute gravitational waves and you get scale invariant, like for inflation, but you get a slight blue tilt, unlike for inflation. So with this stringing mechanism of our universe cosmology, we can do as well as inflation in terms of the data that we have now. In fact, I would argue that we do better because we immediately get the right amplitude without having to stick it in by hand. And we get a prediction for future observations with which we can distinguish the scenario from inflation. So string gas appears to be an alternative to inflation for generating everything we see. It is non-singular, but the Achilles heel is that we do not have a description, a mathematical description of the background. So Sriram, how many minutes do you give me?
Maybe a couple of them, 2 to 3 minutes, if you can wind
couple
up.
of minutes,
We can
okay.
have about
So then I
questions.
will just mention the 2 new avenues that we have been exploring. One new avenue is double field theory, but I will skip over that. And the avenue which we've most recently been exploring with Shudo Brahma and Samuel Laliberté is a model in which we start with a non-perturbative proposal for string theory, which is a matrix model, the BFSS matrix model. So we are starting with a theory without space, a theory, a quantum mechanical model, where all we have is n by n Hermitian matrices. So this is Lagrangian. We have our n by n Hermitian matrices, 9 of them. And we have 1 additional matrix in this covariant derivative. So we have 10 matrices. It turns out that in a thermal state, we can always diagonalize one of these matrices, and this matrix becomes emergent time. The other matrices in the n going to infinity limit become emergent space. So this is a way to visualize these matrices. And what we've done is we've computed the thermal correlation functions in this matrix model. And we find the same results as in string gas cosmology. So this very wild idea, which I don't really understand completely myself at the present time, in which we are working on, is this wild idea that the non-perturbative definition of superstring theory will yield emergent space, emergent time, and an emergent early universe cosmology. But obviously this is extremely speculative, but the bottom line is that there is definitely going to be a connection between string theory and early universe cosmology. So let me jump to the conclusions. So the robust part of my conclusions is the following. We have lots of data about the cosmos, and much more data is expected soon. And all of this data can only be explained by invoking new fundamental physics in the early universe. So string theory, early universe cosmology. The current paradigm we have is cosmological inflation, but cosmological inflation suffers from conceptual problems, and we have alternatives to cosmological inflation. So these are the robust part of the conclusions. Now, the speculative part of the conclusions are that superstring theory yields alternatives to inflation, which makes specific predictions for upcoming experiments. String theory makes specific predictions for experiments. I want to emphasize this. And then this last point. So now I have one more slide, and this is for the new center. So I hope to have convinced you that cosmology, universe cosmology, needs string theory. And if you want to test string theory needs cosmology. And given this, I will wish the new Center for Strings, Gravitation, and Cosmology lots of success. And I hope you'll be able to turn the wild ideas that I presented at the very end of the talk into something more robust. So thanks a lot for listening, and I will go back to the main conclusions.
Thank you. Thank you very much for your talk, Robert. It was a wonderful talk. I open the floor for questions. The best is to raise your hand, and I can then call you to ask your question. Ian, you have a question. Please proceed.
Hi, Robert. Thanks for this great talk. And I have actually a few questions, several questions. The first question is, when you were talking about this Transplantian censorship conjecture, is it supposed to be something that ring is sort of a ring for all these other kind of conjectures? Because Rudelius was claiming that this no eternal inflation conjecture actually kind of already encompasses most of the other ones, like the bound on v prime by v and all of that. So is this Transplantian censorship conjecture also rules out eternal inflation?
Yes, definitely. It definitely rules out eternal inflation. Now, see, I view this Transplantian censorship conjecture as independent of string theory, because I'm really arguing. So the way I'm arguing for it is by generalizing Penrose's argument. So even people who don't like string theory, I think they should pay attention to this TCC. But there are close connections between the TCC and the various swampland criteria. In fact, in this paper, which I have, the paper by Bedroya and Waffa, they already mentioned that you can see the connection between the Transplantian censorship conjecture and the De Sitter conjecture. So in the context of string theory, there are close connections.
Yeah, okay. Thanks. It's a good update then. So another thing is, other is a very basic question. Do you subscribe to the Kremenelli, Senator, etc., this the effective theory of inflation that it could be used for?
No, I'm arguing that it will inevitably break down. So you see, I'm very positive about effective field theory of large-scale structure. So some of the same authors are working on effective field theory of large-scale structure. And I like this a lot. but I don't really see what you gain by effective field theory of inflation, if inflation has these problems. So I think that in order to describe inflation, we need to go beyond an effective field theory description.
So you want
there
to
are
say
ways
that
to-
the computations that we standard do with some scalar field in some semi-classical background that has to be completely revised from scratch in the future?
For
if one
inflation,
to-
yes, unfortunately, I think so. But you know, take this as a good point because there's lots of interest in physics. I want to point out approaches by Keshav Dasgupta and collaborators. So again, Shudo Brahma is part of it. And also works by Dvali and collaborators, where they obtain inflation as a coherent state built on top of either Minkowski or Anthony Sitter space. It's
Chandrasekhar actually, Chandrasekhar actually gave a talk on these things here in IIT Madras on this.
Maybe we can ask whether the students have questions, and then we'll come back to Robert.
Yeah, I just have a very short question. So
Sure.
to enter, so what actually then we should? I mean, if suppose we want to revisit this original computation that we do with a scalar field in a semi-classical space-time, is there some effective ways we can improve this computation? And what I mean to say is that if there is indeed some kind of a hierarchy between the scale of inflation and the Planck scale, right? Would you expect that you should be able to give some ways to improve the current computations people are doing in some systematic manner?
Yeah, so let me go to this slide here. So from the Transplant censorship conjecture, and from this slide, I argued that you have a upper bound on the energy scale of inflation. And now, if you are able to construct such a model of inflation which satisfies this bound, then there are things to do at the level of effective field theory. But then the challenge that I would give you is you then have to work on initial conditions. Can you get initial conditions without fine-tuning for this low-scale inflation? So you wanted a suggestion of what to do at the level of effective field theory, and this is what I would suggest.
So that's exactly what I was thinking. You have to work on the initial conditions, and that is
right.
And this is what your any UV complete modeler is going to tell you, like how to initialize inflation.
That's right. Well, it might give you,
Thanks.
I think it will give you something different, but it might give you inflation.
Thanks. Yeah.
Thank you, Ian, for your questions. Are there any of the other participants would like to ask a question? You can unmute yourself and ask the question.
Sriram, can I ask?
Yeah, go ahead, Ratul. Please speak loudly.
Yeah. So as I understand from your talk, the string case cosmology as a constant scale factor in the very early universe, right? So
that's the postulate.
Okay.
That's the postulate. Now, let me go.
Yeah. My question is, so is as I understand from some other papers like Aquarotic scenario, that also has almost constant scale factor during the contracting phase. So can we go from Aquarotic scenario to string case cosmology by approximating like A is almost constant or something?
See, actually for Aquarotic cosmology, this is slow contraction. Mm-hmm. And I consider the Aquarotic cosmology to be a very interesting scenario. If you work in terms of bouncing cosmologies, I think it is the most promising one. But you see, in the Aquarotic scenario, you don't get a thermal state on large scales.
Okay.
So I view the Aquarotic scenario as an alternative, a promising alternative. In fact, I could have given a separate talk on this scenario as well.
Okay, okay. Thank you.
Thank you, Ratul. Are there any other questions? Are there any questions from students? Kindly unmute, and Chandra, you wish to ask a question?
Yes, Ram, a very quick one.
Sure.
Yeah, so I wanted to know, I saw this tail of the black body radiation curve, and it is around 20 centimeters or something. So I just wanted to ask whether the 21 centimeter observations can also tell something about the very early universe cosmology?
Yes, I hope so. See, and the reason why is that once we have big 21 centimeter telescopes that can provide maps, then we can map out the distribution of baryons in the period of the early universe when before the universe becomes nonlinear, before the density perturbations become nonlinear. So high redshift 21 centimeter experiments give a good way to make predictions from theories for the data which are independent of nonlinearities.
Okay, so there will be impacts on 21 centimeter line from early universe processes.
Right, so let me be a little bit more specific. So what's happening is that the microwave radiation, this cosmic microwave background, is being absorbed by neutral hydrogen at a wavelength corresponding to 21 centimeter. And so by looking at the distribution of the amplitude of absorption, we can get the distribution of hydrogen in the early universe.
I see. Thanks.
Thank you, Chandra. Are there any other questions? I would urge the students to come forward and ask questions if you have any. Okay, if there are no other questions, Robert, I have a couple of questions.
Go ahead.
Yeah, my first thing is about the emergent universe scenario. Do we understand the kind of spectra and their amplitude that will arise in such cases?
Okay, so you have to give me a model, a realization of the emergent scenario. And yes, so string gas cosmology is an example of this. And so here I'm telling you exactly how to do the calculation. In the emergent phase, we compute the matter fluctuations. Okay. And then we convert the matter fluctuations to metric fluctuations on each scale when the scale crosses the Hubble radius. And then we evolve using the usual equations. So let me go to the next slide. So we want to compute the curvature perturbations and the gravitational waves. And the perturbed Einstein equations give us these relations between the density perturbations, which we've computed in the emergent phase, and the curvature perturbations, and the off-diagonal pressure perturbations and the gravitational waves. So now in the specific realization of string gas cosmology, we know what these are. We know both the amplitude and the slope. And it's a function of the string, of the temperature of the string gas and the string scale. But then in this, I argue that this temperature is very close to the Hagedorn temperature. So then we do the calculation. So the density perturbations are given by the specific heat capacity. This is your general formula. R, that's the scale, that's the length scale. And the stringy input is this. This is the holographic scaling of the specific heat capacity. And here you see the string length appearing. And here you see the deviation from the hydron temperature.
Understand.
And then you plug this in, and this is what you get for the power spectrum. Every step is contained here. I'm not skipping any step.
I understand. And what determines the tilt? You said that you are able to get a red tilt.
That's right. We cannot compute the red tilt, but we can argue that the tilt is red. But now, given the red tilt, we can compute the blue tilt of the gravitational waves. Because you know the tilt is given by how fast the temperature changes as a function of K. So it's the K dependence of this temperature. So the temperature is roughly constant when modes exit the Hubble radius. There's a very slight K dependence. And this very slight K dependence, it gives us the red tilt for the curvature perturbations. But you see it arises here in the numerator, not the denominator. So it gives you the blue tilt.
I understand.
So we fit the red tilt, but we predict the blue tilt. In fact, we predict the tensor to scalar ratio as well. So with these calculations, we have 2 degrees of freedom, and we fit 4 numbers.
What will be the typical tensor to scalar ratio?
It will be about 10 to the minus 4.
Okay. All right. So my last question concerning bounces. What is the status in terms of avoiding the difficulties of evolving perturbations across bounces?
Okay, so let me go back to this, because I can illustrate the difficulties in terms of this graph. So what you're asking is, what are the difficulties in evolving fluctuations through this T=0 surface? So again, if you look very carefully, this is H=0, Hubble radius infinite. So the Hubble radius actually goes to infinity. So every scale is actually, for a very, very brief time, it is sub-Hubble. So the statement is that the answer that I will give to your question is, we cannot make any model independent statements about how perturbations evolve from just before the bounce to just after the bounce. We have to study the physics carefully. If we work in the context of a non-singular model, of a non-singular bounce where this transition is smooth, then there are many models sort of give us the result that on infrared scales, the spectrum is unchanged between just before and just after the bounce, where infrared is relative to this time scale. And
you will achieve that with some spatial curvature, is it?
No, I definitely don't use spatial curvature for that. Because you see, spatial curvature becomes less and less important compared to other stuff when I go close to the singularity. So spatial curvature is not what I would want to use.
I understand. And where do you believe, in the case where the Hubble radius blows up at the bounce, there are some cases I see where they impose the initial conditions at the bounce. Do you think that is valid rather than imposing in the sub-Hubble domain at very early times?
No, from the point of classical physics, and it is classical physics which is used to compute the fluctuations. From the point of view of classical physics, it makes absolutely no sense.
Okay.
I'm making a very strong statement here.
Okay.
So I strongly disagree with doing this.
Because in some loop quantum cosmological models, they evaluate when they impose the conditions at the bounce in that case.
I know.
Okay. Okay.
And this is very controversial within that community.
I understand. Okay. Thank you, Robert.
Now, you see, what I really believe is that if you want to make a successful bounce in cosmology, again, you can look to string theory. And we have a proposal for the S-brane mediated bands.
I understand. I understand. Thank you. Let me just check one more time if anyone else has a question. K7, would you like to ask a question? Is there anyone who wishes to ask a question to Professor Brandenberger? Okay. There doesn't seem to be any other questions, Robert. Thank you. Thank you very much for joining us today and giving this inaugural Chandrasekhar lecture. We will remain in touch. And as I had said at the start of the lecture, we are hoping that you will be able to visit us sometime soon and spend some time with us. Thank you very much.
Thank you again, and good luck with the new center.
Thank you. We'll keep you posted. Thank you, everyone, for joining. Bye-bye.
Bye.
Bye.
Great. I have to prepare for my class now.
Oh, I understand, Robert. Thank you. Bye.
So thanks again, Sriram.
Bye. Thank you, Robert. Thank you for joining and giving